All right, cool. I think we'll get started. So, no America's Got Talent. I assume you're here because you want to build an incident response stack using OpenTelemetry. Thanks once again. I really appreciate it. You're here on a Saturday evening. It's the last talk. I'll try to keep it interesting. Cool. So we'll start off by setting the agenda. We'll begin with an intro to IRM, and we'll talk about why it's needed and the different components of IRM. Then we'll go over to OpenTelemetry and its principles. We'll discuss how IRM fundamentally relies on OpenTelemetry and using observability data and the different telemetry signals. And finally, we'll talk about some helpful query patterns for our telemetry databases and solutions we can build on top of these. So a little bit about me before we get started. That's me over there at a Grafana offsite. I've been at Grafana for about 3.5 years now. This is from Whistler, a couple miles north of here. I am the co-creator of Tempo, which is our distributed tracing database, and now I work on the ML squad, where we're building solutions to reduce the on-call burden for SREs. I stay in Seattle, and as of last week, I have a new hobby. I build custom signboards. That's one that says Grafana Way. So, if you want to talk about vinyl cutting machines or OpenTelemetry, I guess you can hit me up after this talk. So cool, let's dig in. What is IRM? So we'll start off with a quick show of hands. How many of us have been on call for production services? Sweet. Okay, so y'all can help me verify this very scientific chart I made about the software development lifecycle. It's like just tracking happiness over time, and it's all downhill after building features. And like jokes aside, on-call duties are extremely important, right? Like I personally learn a lot about our systems when I'm on call. And there's a very interesting report on this website. It's called snafugcatchers.github.io. And it's funny, a bunch of researchers and practitioners met up in New York, I think, and they were talking about the components of IRM. And coincidentally, they were hit by a snowstorm, and it was called Stella, so they named the report that came out of it Stella. And it basically says that current generation internet-facing technology platforms are complex and prone to brittle failure, and without the effort of on-call engineers, they would stop working mostly within a year, right? And as on-call engineers, we can confirm that things go wrong all the time, like disks run out of space, DNS resolution fails, bad releases break backward compatibility, and the list is endless. And when things go wrong, we have to keep the system architecture in mind, and we have to interact with monitoring tools to debug the issue, and coordinate with other people because the issue could be happening with the authentication team that's impacting all other teams, or like the platform team rolled out a MySQL upgrade that broke everything. And there's just like so much cognitive burden on the mind, right? And there was a really interesting human factors study in 1995. It's a little old, but it's still valid. And it talks about situational awareness and decision-making when humans are subjected to stress. And the findings are really interesting. Maybe if you've been in an incident, you can relate. But when humans are put under stress, fine motor skills go out the window. So things like talking, typing can become really hard. Field of vision narrows, so like literally all the ultra-wide screens are pointless at this point. Our short-term memory is often short, so any run books or architecture docs that you have in mind, you can't really keep track of them. And there's a bias to make decisions faster and with incomplete data. And during this time, we're tasked with coordinating all of this, right? And when you're a smaller company, it's easier to do it because you can just like use a megaphone since everyone has open floor plans anyway. But companies grow and architectures get really complex. This picture right here is from Uber's microservice architecture mid-2018, so this is like 6 years old. And it was generated from Jaeger, which is their homegrown distributed tracing system. And you can already see how complex it is, right, to coordinate efforts across teams and time zones. Like, for instance, who owns that service? Like, what are its KPIs or SLOs? Where are its runbooks? Why is it logging this weird message, right? We don't know anything about this. And the panic makes everything worse and difficult to coordinate. And this is why we do drills. Drills can feel really annoying at first, but they teach us exactly what to do when things go wrong. humans don't necessarily reason well under stress, so we need to be conditioned to it ahead of time. And this is why we go through this process multiple times and we have a refresher course. And so as a company grows, it needs an incident response playbook, right? This defines what an incident means for the company and the set of procedures to follow during such an incident. So internally, we've defined what an incident means to us based on the Google SRE book that's linked at the bottom. So we define an incident when there's visible impact to customers, or there's a coordination needed with a second team, or it's unresolved after an hour of concentrated analysis. But this incidents could mean different things to different companies. If you're working with financial data, maybe an hour of concentrated analysis is way too long. Even a minute of outage is an incident at your company. And then incident response is the processes we follow when something unexpected happens, right? So not just do we now need to define what incident response is, we also need to define roles. So internally, we have these two, which is a commander and an investigator, and they have like really split goals. So the job of the commander is to coordinate with the rest of the world about what's breaking within the system. So they're tasked with like updating the status page, coordinating with customers about what's going wrong, talking to other teams, and they have to shield the investigator from doing the real debugging. And the investigator will actually like look at monitoring tools, try to debug what's going on, and move the incident resolution forward. And once we've defined the roles, we also need to come up with tools that each of these roles will do, right? And like importantly, don't think like you don't have the tools already. They just need to be documented in a place with a procedure that the whole company can follow during an incident. So there's two kinds of tools for the commander. One is communication tools to coordinate with other teams. And then there's documentation tools. These are used to store evidence so that we can prevent the same incidents from repeating in the future. These documents are either called like, I don't know, they have different names. They're called like postmortems. We call them post-incident review documents. But the idea is the same. You kind of gather enough evidence so that you can prevent such incidents in the future. And so we spoke about like the tools available for the commander, and now we'll talk about the investigator and what tools are available. So this is what brings us to OpenTelemetry. So if you've read the abstract, you probably would have guessed that was a segue, but of course everyone reads abstracts. So if you've been on call, you've probably been in a war room like this. This is from Zomato, which is a popular food delivery system in India, and this is from their CEO tweeting about the preparations for expected spikes in orders on New Year's Eve. And engineers in these rooms will look at observability tools. What is observability, right? Where do I start with observability? Do we just set a bunch of money on fire? We'll start off with the basics instead. So we'll start by monitoring core resources that everything else depends upon, right? CPU, memory, and networks. And we'll monitor these for our Kubernetes nodes, database services like MySQL, and so on. Then we'll move on to basic services like Nginx or Istio that are sort of fundamental for other services and that other services depend on. And finally, we'll monitor CI/CD also. And this is like a really cool trick that we started using internally. For every service that we run or every pod that we run, we started emitting a metric with all of the build information. So it has things like the image version that the pod is running, the Go version, what branch it's built off of. And that's been super helpful to know what versions of our software are running in different clusters. We can also monitor rollouts that way. This can already give us a lot. And also, does anyone remember Clippy? Okay. The Prometheus community, the Prometheus community has written a bunch of like exporters for commonly used software already. So you could already go install this and run this on some really popular software. It's available at this link. Next, for applications, so the services that implement business logic, we can start using OpenTelemetry, which has become the standard of choice. There was a talk literally right before this where a lot of these concepts were also spoken about. So OpenTelemetry, I took this from their website. It's a collection of APIs, SDKs, and tools. use it to instrument, generate, collect, and export telemetry data to help you analyze your software's performance and behavior. OpenTelemetry is generally available across several languages and is suitable for use. So that's a lot of words. Let's start with APIs and SDKs. Okay, so these are instrumentation points within application code. Right? These are the main points of interaction between the application code and the whole observability stack. As a developer, OpenTelemetry aims to make it as simple as possible to instrument your application so you can focus on the core business logic. Right? So what does this look like? So here I have like a very simple Golang app. I took it from their examples repo. And so you can see the SDK and the API in action here. So an SDK is a very simple OpenTelemetry library that you import in your applications. And the API is how you interact with this to create the telemetry of your choice. So in this case, we're just like starting and ending some spans. But the function definitions and all of that has been already implemented by OpenTelemetry, so you can just focus on writing the core business logic, right? And so while this example was for Golang, but OpenTelemetry has stable SDKs in a lot of languages. You can just pull and use them. The metrics and logs SDKs are, like some of them are still experimental or in development, but most of the tracing ones are stable, except for Rust. Cool. We'll move on to tools. So tools are things like the OpenTelemetry collector and other auto instrumentation libraries. I think they have something for Lambda, so you can run auto instrumentation for Lambda functions if your code's written in Java, JavaScript, and Python. I think these are the three languages. So what does the OpenTelemetry collector do? The collector is, it's actually very interesting and it warrants a talk of its own, but it's a flexible data pipeline component to collect and enrich telemetry data. It also has custom processors, so you can do things like attach the same labels to the different telemetry signals that you're collecting. So internally, we attach the same cluster, namespace, pod, and all of these like resource labels to metrics, logs, and traces. So we have a consistent experience across them. The collector also does like sampling, routing, authentication, retries. It's like a really battle-tested pipeline tool to route data to a backend of your choice. So yeah, again, all the links are available, and when the slides come out, you can grab them. And now we'll come to the signal types. So we hear so much about metrics, logs, and traces. So currently, metrics, logs, and traces are supported by OpenTelemetry, and like a week or two ago, the profiling proposal has been merged into OpenTelemetry, so it's also coming soon. But why do we hear so much about metrics, logs, and traces, right? Like, why specifically are these three chosen? They all serve different purposes. That's kind of why they're chosen. Metrics are aggregatable and pack the most amount of information per byte of data transmitted. These are great to get an overview of the system and hone down on the problem to some extent. Traces, on the other hand, follow the path of a request as it goes through multiple microservices in your system. And these require context propagation through different components to stitch together spans and form one single trace on the back end. Logs, on the other hand, are human-written descriptions. I don't know what logs are. Among the three signals, logs have the highest volume because this could include events that are not request scoped, right? Like when the process is booting up, it could be like reading a write-ahead log or logging some initialization details. So all three of these signals capture different contexts that are helpful during debugging. But again, like this list need not be exhaustive at all. There can be more signals. Continuous profiling is another such one that's recently become quite popular. It helps finding and debugging painful performance issues down to the function and line of code. Like these flame graphs have been around for a while, but yeah, again, they've become recently popular, and a couple of open source solutions have also come up in this space. There's like Pyroscope, Polar Signals, and a couple of others. So I think this part of OpenTelemetry doesn't get talked about as much, but semantic conventions are pretty important. These define a set of attributes that provide a specific meaning to data when instrumenting applications and querying. For instance, like I have 4 services here, and they could be owned by different teams, and they'll all name it differently, right? Because humans are inherently different. And naming is hard. And like this can break a lot of queries and correlations between metrics, logs, and traces. So how do we fix this? OpenTelemetry has a list of standard attribute names that you can use for special things. So DB connection string, there's now a standard way to use these labels across all of your telemetry. So if you're instrumenting your app, make sure to look it up in that list that OpenTelemetry has already. And finally, we'll come to query patterns and building the stack. So far we've seen instrumentation and the data pipeline, and that's where the OpenTelemetry specifications and implementations end, right? That's the boundary of OpenTelemetry. Beyond that, it's like a bring your own storage kind of situation. And there's a lot of open source solutions, or even vendors if you want to go for those. What kind of patterns should we care about while choosing a database for our telemetry? We'll look at some examples from PromQL, LogQL, and TraceQL because these are open source languages. Like the most basic thing I would expect out of any metrics database would be to chart a metric over time, right? This query here is a simple rate query over a counter that's plotting the number of requests per second received by a service called query frontend. And these are like literally building blocks of all dashboards. So I'm gonna skip to the next one. This is where it starts getting a little interesting. Another query pattern is aggregation based on different labels. And so this query answers how many requests per second is my query frontend receiving on each cluster and namespace combination. Fundamentally, what this is doing is it's throwing away all the labels that I don't care about. Like that metric could have pod and like 1,000 other labels that I don't really care about. And if I have multiple pods of the same service deployed in a cluster, I might want to sum them all up to get the total requests in the cluster rather than seeing the individual numbers. So these kind of queries or aggregations help doing that. Percentiles are another important instrument we use while monitoring systems. So I wouldn't worry too much about the query itself here. These are just semantics of the query language. But what's important is the kind of information it's giving us. So this query helps me find the 95th percentile latency for all API endpoints that start with tempo_API on my service called query frontend. So now, depending on your application, you might want to track different percentiles, but 95th percentile gives a pretty accurate picture of the performance of the system. So this is another useful tool. We'll move on to logs. So again, like we'll start with the basics. Like the most basic thing I want a log database to tell me is, I want to grep through my logs in production. Like, did this particular keyword occur in my logs, right? And this is the kind of query that should let you do that. A really helpful query pattern that's been useful to us is spotting trends for a given search term. So if I find an error message in logs, I want to understand when it started, how long it's been happening, has it recently increased, and all of these statistics about it. And this is super helpful in debugging. So here's a query that just does count over time, and it just helps me plot the rate of the keyword over time. And so this is kind of getting into metrics from logs. So this is also an interesting query pattern. And lastly, the logging database should have an extensible schema and allow me to query fields that weren't initially indexed, right? So I would not want to index on a label like client IP because it's just so high in cardinality that it would like bloat up my index. But I still want to query for it after I've narrowed down the scope through some label selectors and a time range, right? That reduces the data volume of my query, and now I'm only looking at a subset of data. So that's what this query is doing. So we're saying we're going to select all logs based on these label selectors and then pass it through a log FMT processor, which basically discovers key value pairs that are present on my logs. And then once those key value pairs are discovered, it allows me to search through them. So I'm searching for client IP for a very specific one. So that kind of helps me spot that. Cool. We'll move on to traces. Again, simple queries. We'll start with show me all traces belonging to a cluster and namespace that have high latency. This is like the most common trace query that we would start with. Then we'll move on to querying based on the structure. So using TraceQL, you can query the structure of the trace. In this case, I'm trying to find a trace which has one span with HTTP route set to API failing, and a descendant span in the same trace that has status equal to error. Now I can get really creative with this when I get the power to query the structure of the trace, right? So I can say, find me all traces that made a call to memcache and then made a descendant call to Postgres. That would mean that it would find me all requests that had a cache miss, because it first went and looked at memcache and then at Postgres to find the actual value under it. So these are like super helpful query patterns. And finally, metrics from traces. Again, spotting trends over time. That's kind of what we want to do. This particular pattern, if you worked with metrics, you've probably heard that cardinality can be a big problem. Like, you don't want to store labels that have high cardinality. You've probably been told, do not add customer ID on your metrics because a per tenant ID can be costly. But tracing databases have that information, right? And they should be able to generate metrics based on these arbitrary labels on the fly. That's what this query is doing. So here we're finding all error traces from the clustering namespace, and then using a rate function to generate metrics grouped by tenant. This is very powerful. It gives error trends for each customer. And then from here on, what I can do is I can look at that generated metric, and I can find the customer that's been having most errors. And then I can include that customer ID in my selectors, and then rate by a different label, group by a different label, and find metrics based on that. And then now I'm seeing all HTTP API endpoints for a given customer ID and seeing the trend of errors over time for that particular endpoint. And once I find the problematic API endpoint, I can group again by a different label, and I can keep doing this until I find the right combination of labels that's triggering the errors. Yeah, so that was some helpful query patterns that we have seen. But once you have these query patterns, you can do some really cool things. Like, you don't have to stop there, and you can build things on top of these. So remember the slide about motor skills going out the window? Like, while it is great to have raw telemetry data, purpose-built tools and automation can help greatly during incident response, right? We might not want to, not everyone might be able to write structured queries during an incident. So one of the things that we do, let's start off with the simple one, right? Like, is alert on the right data. So it's super important to alert on symptoms and not causes. Do not alert on a restarting pod. It will auto-recover. On-call engineers are already stressed. We should not be adding alert noise. We should be like reducing alert noise as much as possible. And for this, we need to find metrics that indicate user impact, right? These are called SLOs, or service level objectives. And we can use these to alert only if a customer is facing issues while using the service, and not if an underlying system is breaking, because we know that it'll auto-recover. And once we have these SLOs, these are usually implemented by like a central observability team. You can drive adoption using this. So an interesting story is internally at Grafana, our CTO, Tom, wanted to drive SLO-based alerting, and he found an interesting way to do this. He started sending out a weekly report with SLO metrics to the whole engineering team, and that way, like, everyone started optimizing for SLOs, and those who weren't on the report wanted to get added. So that was like a neat little way to start driving adoption. So this is something that you can use internally based on this. Second thing we can do is build debugging workflows with knowledge of what the app does, right? Every app is unique. Front-end engineers care about time to first byte and first contentful paint, I think. I learned it while I was doing my research for this talk. And backend engineers care about red metrics, like request errors and duration. And so designing the debugging workflows with knowledge of the app in mind can make the user experience so much better during incidents, right? Like, build dashboards and experiences that have knowledge of the underlying app. And again, going back to how can we help users in incident response? What users really want to know during incidents is what changed, right? Query languages can help make this process easier, but what if we could automate it? And in this case, we have an example where we can see an SLO burn alert, and you can see the SLO metric dip. And we've automatically surfaced error patterns in the logs that started around the same time when the SLO metric dipped. So we can start automating a lot of these. And so this, by the way, is based on the drain algorithm, which is also available on this paper at this link. So yeah, we've implemented drain internally, and using that, you can start surfacing error patterns that occur during a particular time and start correlating that with a drop in your SLO metric. You can do the same for traces. Like, traces are known to be notoriously difficult to scan to detect changes, especially traces that can have more than 100 spans. It can be difficult to identify the changes just by looking at them individually. But yeah, we looked at some change detection techniques in the TraceQL query patterns. So I'm going to skip this one and go into metrics. So in this case, we're running what's called change point detection. I know those slides are probably not super clear. But change point detection is a method to identify changes in a time series by analyzing its patterns over time and finding any deviations from the norm. So I have a global SLO metric at the top in this example. I think it's Cortex reads high latency, yeah. And the panel below it is showing its performance in each cluster. So the top one is the global one, and the panel below is just split for each cluster. And using an open source algorithm from DataStax, actually the library is again linked at the bottom, it's called Hunter, that's the library. I'm able to automatically detect which of the underlying clusters the SLO burn is coming from. And it may seem really obvious to the human mind, like we are able to process a lot of information by looking at a dashboard, but doing this automatically is pretty challenging. And this is also an interesting automation that can help on-call engineers. So, yeah. And finally, using these query patterns, we can also do metric forecasting. So this screenshot is using the open source Prophet library from Facebook, and that's also linked at the bottom. And this is also what we use in Grafana Cloud for our forecasting features. And this library is really good at finding periodic trends that are common in most systems, right? Like in this example, you can see the peaks during weekdays and the flat lines on the weekend. So the Prophet library is really good at finding these kind of trends. And this can be really helpful to provision resources ahead of time or find like unexpected changes in your system. So another tool that you can build on top of those query patterns. There's more to do, like outlier detection, but I think I will wrap it up here. If you found any of these useful, we're building a lot of open source software. You can come talk to us at our booth or in our community calls. Yep, I will wrap it up there and take any questions. Thank you. Too good. Just got everything right. It's been a long day.
Lucky you.
Thank you so much. Thanks again for coming.